Hi everybody, this is the first of two videos that will cover section 4.2, and here we are going to talk about linear equations and augmented matrices. And I guess the first question is, well, what is a matrix? Well, here's your answer. A matrix is a rectangular array of numbers that are enclosed in brackets. Here is one matrix. Notice here it has 4 rows and 2 columns. The matrix has a name. Yep, it's A, and it is a 4 by 2 matrix. This matrix has 4 rows and 3 columns, and it has a name. It's called B. And this matrix is a 4 by 3 matrix. Notice that the dimensions of the matrix is specified first by the number of rows and then second by the number of columns. Now each number inside the matrix we call an element. And as I mentioned before, when we specify matrices, rows, columns, which is kind of like what I'm saying down there. Now we do have some special matrices. This matrix here is a 4 by 4 matrix, and it has the same number of rows as it does columns, so it kind of looks square, and hence it is called a square matrix. One feature about this matrix, or important part of this matrix, is this diagonal right here. And we call this diagonal the principal diagonal. Now, if a matrix has exactly one column, we will call it a column matrix or a column vector. And if a matrix has exactly one row, we will call it a row matrix or a row vector. And this brings us to our first example, where we need to determine the size of the following matrices. So here we go. Here for part A, notice that we have 1, 2 rows and exactly 1 column. So this is a 2 by 1 matrix, 2 rows, 1 column. This has 1 row, 2 columns. So this would be a 1 by 2 matrix. And then finally over here we have 3 rows, 2 columns. Right? And once again, rows are always first. So this is a 3 by 2 matrix. Okay. And so since a matrix is essentially a rectangular collection of numbers, we need to come up with a concise way to identify certain numbers at certain positions. And to do that, we use a double subscript notation, okay, where the first subscript determines the row position and the second subscript determines the column position. So obviously this is the first row, first column, first row, second column, second row, second column, second row, third column. And once again, the elements that for this really only applies to square matrices, but the elements that have the exact same row and column identifier make up the principal diagonal. And that brings us to this example. Let's consider this following 2 by 3 matrix. And we want to identify the elements A23, A11, and A31. Well, A23, that's second row, third column, that would be this number right here, -9. A11, first row, first column, that would be 2. A31, that would be the third row, first column. Well, there is no such element, so this does not exist. Okay, now for example 3, we want to find the principal diagonal of this matrix. Remember, the principal diagonal of a square matrix is this diagonal right here. In other words, all the elements that are defined by AII. First row, first column, second row, second column, third row, third column. So the principal diagonal are the elements 5, -5, and 3. Okay, so why do we care about matrices? Well, we care about matrices because they provide a shorthand way of representing and solving linear equations. And they are the foundation for all computer-based and, by the way, calculator-based solutions for linear systems. And let's take a look at this linear system right here. Okay, now if you've noticed that when in our previous section, when you've been solving linear systems, we don't really mess with the x and the y's. We only mess with the coefficients. The coefficients are the thing that we manipulate. The x's and the y's, they stay the same, and they are more or less like position indicators. So as a consequence, we basically only want to mess with the coefficients, and the matrices allow us to do that. And we have three important matrices. One, we have the coefficient matrix, 3, -4, 3x, -4y, 2, 5, 2x, 5y. So the first column is kind of associated with the x variable. The second column is associated with the y variable. First row is the first equation, second row is the second equation. The constant matrix, which is associated with these two terms, and once again, first row, first equation, second row, second equation. And then the augmented matrix, where we actually concatenate these two together and have a vertical line to separate the coefficients and the constants. And notice the correlation between the equations and the matrix. First row, first equation. Second row, second equation. So here we have 3x minus 4y is equal to 7. 2x plus 5y is equal to -2. And you need to get used to the idea of having this represent that. In other words, you should be able to look at this and write the augmented matrix. And on the other hand, you should be able to look at the augmented matrix and be able to write the associated equation. It's very critical that you get used to doing that. Okay, and this is the generalization of the exact same thing we talked about. Here's our first equation, a11 times x1 plus a12 times x2. We're using x1 and x2 instead of y is equal to k1. So the first row is going to be a11, a12, k1. Similarly, we have a21x1, a22x2, and k2, a21, a22, k2. So once again, you got to get used to being able to go back and forth between the equation and its augmented matrix representation. Now recall that in solving systems of equations using the elimination method, we actually had three transformations that would form equivalent equations. We could either interchange the equations, we could multiply the equation by a non-zero constant, or we could take a constant multiple of one equation and add it to the other equation, and the result would be an equivalent equation. In other words, an equation with the exact same solution set. Well, in terms of augmented matrices, they are these are the equivalent operations. Suppose we had the system x plus y is equal to 2. And then 2x plus y is equal to 3. Okay, well, as we mentioned before, the corresponding augmented matrix is going to be 1, 1, 2, 2, 1, 3. Will look like that. Now, in our previous slide, we can interchange two equations. So I could write this as 2x plus y is equal to 3, and then x plus y is equal to 2. We've done absolutely nothing here. Well, that's the exact same thing as going 2, 1, 3, 1, 1, 2. There you go. Now, in the previous slide, we mentioned that we could take an equation and multiply it by a non-zero constant, say 2, and that would be an equivalent equation. We would then have 2x plus y is equal to 3, and then we could have 2x plus 2y is equal to 4. These would be equivalent equations. The solution set would be the same. Well, that would be the same as multiplying this by 2 and just putting it back in that particular row. And that would give us 2, 1, 3, 2, 2, 4. So we pretty much did the exact, so what we did here is the same as what we did here. And then finally, we could add these two together, and that would give us 4x plus 3y is equal to 7. We could have that be our first equation, and then we can come back and have x plus y is equal to 2. These would be this would still be an equivalent system. And the augmented matrix associated with that system would be 4, 3, 7, 1, 1, 2. And notice that what we have here, we have equation transformations, and here we have what we call row operations. And we're going to spend the rest of this video talking about these row operations. Now, the first thing I want to mention is that the first operation is interchanging two rows. And the double arrow means that we are basically going to swap the rows. Now, this one says we're going to multiply the row by a non-zero constant. So what we're going to do is we are going to take the ith row, multiply each element in that row by k, and put it back into the ith row, which is essentially what I did here. Notice here, I did not change row 1, but I took row 2, multiplied it by 2, and put it back in row 2. And then here, I took row 1, or 2 times row 1, plus row 2, added them together to give me this, and I put it back in row 1. I probably should not have used that there. And that is the idea behind row operations. And we're going to work on this in the next couple of slides. And here we go. Okay, here we want to perform the operation switching row 1 with row 2. That's specifically what this means. We want to take row 1 and row 2, and we want to swap them. And if we do, then our new matrix is going to be 6, -9, -8, 1, -4, 6. Vertical line. And our brackets. Now this one, example 5, this is what this says. It says take row 2, multiply each element in row 2 by -2 and put it back in row 2. Now the question is, so this is our operation, and my question here is, what happens to row 1? And the answer is absolutely nothing. Row 1 stays the same. So row 1 is still going to remain 1, -3, 2. But now for row 2, we're going to take 4. We're going to take our first element, 4, multiply it by -2, which will give us -8, and put that back into row 2. So this will be -8. We're going to take -6, multiply it by -2, which will give us +12, and put that back in the second element, or in the second column. This will be 12. And then finally, we are going to take -8, multiply that by -2. That will give you +16, and put that on the constant side. And that is what our new matrix is going to be. Once again, it is the equivalent matrix. It will provide you with an equation with a system of equations with the exact same solution set. Therefore, accordingly, an equivalent equation, or an equivalent matrix. Now here, I want to take row 1, I'm going to add it to row 2, and replace that with row 1. So the question here is, what happens to row 2? Nothing happens to row 2. Row 2 stays the same. So we can just go ahead and write down row 2 right now. That's going to be -2, 9, -3. Now for row 1, we are going to take row 1 plus row 2 and put that back in row 1. And we're going to do this element by elements. The first element is going to be -7 minus 2, which is -9, and that will go here. Here we will have 9 plus 1, which is 10. And here we'll have 8 plus -3, which is 5. That goes there. Draw our vertical line, our brackets, and there we are. And now for this one, we're going to take row 1, multiply it by 5, add it to row 2, and replace it with row 2. So nothing happens to row 1. So we can just go ahead and write that down. 1, -3, 2. Now for row 2, we're going to take row 1, multiply it by 5. So we'll have 1 times 5 plus row 2, which is 4. So 1 times 5, which is 5, plus 4, which is 9. We're going to put that back in row 2. So we're going to have 9 here. Now here, we are going to take -3 times 5 will give us -15, plus -6 will give us -21. And then finally, we're going to take 2, multiply it by 5, that will give us 10. Subtract 8, that will give us 2. That would be our new augmented matrix. Okay, I'm going to do a quick walk through this since this is kind of a short video and talk about why we care about solving linear equations using augmented matrices. Now, if you remember, our goal when we had equation transformations using the, in the previous section, was to try to get x1 equal to something, and then use one of the original equations to figure out what x2 is. Well, in this particular case, our goal is to use the row operations, which is just the same as equation transformations, to get a matrix of this particular form. And why is that? Well, remember, once you have in this form, then what we have is 1 times x1 plus 0 times x2 is equal to 3. What does that tell you? That tells you that x1 is, well, that tells you this. That tells you that x1 is equal to 3. And then we're going to have 0 times x2. And then the second row says 0 times x2 plus, x1 plus x2 is equal to -2, which tells you this. Okay? So the idea here is to get this into this particular form, which is what we call the row-reduced echelon form, or the reduced echelon form. And if once we get it to this, either the solution will be obvious, or it will be obvious that there's an infinite number of solutions, or it will be obvious that there is no solution at all. And that is going to be the subject of our second video. So I hope you're waiting with bated breath to learn all this fun stuff, and I will see you at the beginning of the next video. Once again, if you have any questions, please feel free to contact me. This is Bob Boyle, signing off.